So welcome back for this lab session. So in this tutorial, we are going to cover several different things about VPP. It's not intended to be complicated nor long, but we have plenty of time. So if you have questions or if anything goes wrong with your setup while we are running the tests, please don't hesitate to ask questions and to interrupt. So what we are mainly going to cover are how to use DPDK interfaces and also how to compile, load, and use a sample plugin. So we are going to start with how to use DPDK interfaces. So this morning, if you have attended Pierre's tutorial on routing switching, you have seen how to create host interfaces. So either type interfaces or IF packet interfaces. So now what we want to do is to do what we want to do in a real use case. So use DPDK interfaces so that we can leverage the high performance of the DPDK framework. So for this, I assume that you all have your setup ready with vagrant. So VPP is expected to run in a virtual machine, and the DPDK interfaces that we will run on should be virtual NICs provided by your VM hypervisor. So if you use VirtualBox, it's going to be Intel NICs simulated by VirtualBox. So here you can see that as with Pierre this morning, I did a little page on the wiki for this tutorial. So please go to this page and follow the instruction as I'm doing the tutorial so that everyone can be at the same moment on the same time. So here is the web page. So if everyone has copy pasted the URL and is okay, then we can start. So to start with, what we are going to do is make sure that the vagrant setup is okay and that we will be able to have virtual NICs on our VMs. So if you have followed the tutorial that is here and here, you should have your vagrant file that provides you with 2 NICs. So this setup is fine for me. We can go with this. So please make sure that this is the case by getting your vagrant file and checking here that you have 1 or 2 NICs and that they are configured to run on the private network. So the private network means that you will have a bridge between your NICs and also an interface that runs on your laptop host. So also what I want you to do is to make sure that promiscuous mode is enabled. So since we are going to do layer 2 stuff, we will want to make sure that the virtual machine will not refuse packets that are for other hardware addresses than the one expected. So if you use VirtualBox, then you need to go here and select your vagrant VM, go to the settings, then go to network. So the first adapter is for the management interface, you know, the one that uses SSH for management. And the 2 other ones are created by Vagrant when you provision the VM and will be our 2 NICs for testing purposes. So please make sure that when you click on advanced, you have allow all in your promiscuous mode entry. And if it's not the case, please reboot the VM so that it becomes the case. So if Vagrant was already running, do Vagrant halt to stop the VM. For me, I think it was not the case, so nothing will happen. And then you can reboot the VM with Vagrant app. So as you see here, Vagrant is configuring 3 interfaces, so as expected. And now we are waiting for everything to boot up. So if you go back to VirtualBox, you will see that the host-only adapter that has been chosen by Vagrant is VBoxNet Zero, so it's the first interface provided by VirtualBox. So if you go in your hosts and do ifconfig VBoxNet Zero, you should see that there has been one IP address assigned to it. And so really we will have a bridge between the host operating system and the NICs that are in our VMs. We can go inside our VM with vagrant SSH. So here we are. Now we will make sure that everything is fine. So for this, we are going to just list the hardware interfaces that we have been provided with. So in my case, I have PCI 3, which is ETH0, which is the management interface. And two NICs have been created, ETH1 and 2, which are on interface on PCI address 8 and 9. So we can see with ifconfig what has been going on. ETH0 used some kind of NAT address to communicate with the VirtualBox, and ETH1 and 2 have been provided with new addresses thanks to the DHCP server set by VirtualBox. So we don't really care about the real interface address that has been set, but we just want to make sure that we keep in mind this subnet. So for me, 172.28.128. So I will just check that from my Mac, from my laptop OS, I can ping my interface to make sure everything is fine. So that's the case for me. So now we know that our NICs are good in the bridge and we can access them from the host. And so we are happy and we can start playing with VPP. So if I start VPP now, and I ask it to show the hardware, as we have explained this morning, we won't have any interfaces except for the local one because VPP will not attempt to use any interface that is already taken by the kernel. So in our case, ETH1 and 2 were up, as we can see here, because they have received an address and the kernel is happy with them. So what we need if we want to use them in VPP is to set them down and to whitelist them in the VPP startup file. So here, I will edit the vpp startup.conf and add the first NIC, so which has PCI address 0000008. So for this, I need to add a new entry, DPDK in the startup file with dev followed by the address. So as you have seen in this example, I also added other arguments like socket mem can be used to tell how many memory you want to use for DPDK. You can also specify the number of mbufs. So this can be seen here. So in the command line argument reference on the wiki, you can see that you can set the core masks, that you can ask not to use huge TLB, and you can set the number of mbufs. You can also switch PCI drivers, as we were explaining a few minutes ago. So I'm gonna ask my VPP to use my the ETH1 NIC. Sorry. and I will restart VPP. So now everything should be fine. So if I go to my VPP CLI and I say show hardware, I see that my Ethernet interface has been taken by VPP. So we can see its PCI address and its MAC address, etc. So now this interface has been bound to DPDK, and it's not visible anymore from the Linux host. So now we can start playing with it inside VPP. So we are going to do something really simple, namely we will ask the interface to go up, and we will assign it an address in the subnet that we have noted before. So for convenience, I'm going to use the same one as before. So right now, I am in this scenario. I have my host, which is running this virtual bridge on which this address is set. And I have my vagrant VM with VPP inside, and VPP has a DPDK interface, which is gigabit Ethernet 080, and which has been set up to this address. So now I should be able to go back to my host, my Mac, and normally, if I ping this address, it will be received by VPP. So you can see that the first ping took a little bit more of time, as I explained this morning. So which indicates that packets have indeed reached VPP. So the Mac sent an ARP to VPP, and VPP is read up. So if you run show error, you can have statistics on many things, and here we can see the number of ARP replies that have been sent and the echo replies that we have sent also. Another way to get statistics is to do show interface and the name of the interface. So here we can see the number of packets received and the packets transmitted, the bytes that corresponds, and so 7 were IP and 1 was ARP. So now also if we do show run, we will see that DPDK is polling, so it has been called a lot. And for each node, we can see the number of times it has been called. So here, 8 times for outputs, and also 8 times for the input as well. So all of this makes sense. We have 7 ICMP echo requests, so that corresponds to what we had. So now, okay, everything is interesting in this, but we didn't do really any forwarding, which is the main purpose of VPP. So now what I would like to do is to connect to the operating system of the virtual machine. So like this morning, create a tap interface so that we can communicate from VPP to its operating system. And thanks to this, we will be able to communicate from the laptop operating system to the virtual machine operating system while going through VPP. So for this, you have seen this morning how to do routing, switching. I want just to show something really simple, which is layer 2 cross connection. So which is a way to plug two interfaces together so that the traffic coming from one is redirected to the other and vice versa. So it's a very simple way to see in our case what will be going on. So I'm going to restart VPP so that everything is cleaned up. I'm going to the CLI and I will ask it to create a tap with name tap 0. So here we can see that the command answered with another name. So tap-0 is the name of the interface inside VPP, while tap0 is the name of the interface in the Linux host. So if you go to the startup configure, you can add this line. So CLI-listen localhost colon some ports, which will enable you to go through telnet instead of VPP-CTL to enter CLI commands. And an advantage of this is that you have a pager, you also have an history, so it's more fancy than just going through the VPP-CTL interface. But compared to the interactive Unix interface, then if you leave the session, you don't close VPP, so you can leave it in the background. So back to our tap interface, we see that, okay, an interface has been created. So now we are going to assign it an address. So still in our subnets. So for instance, .42. And what we are going to do is to cross-connect the DPDK gigabit Ethernet interface with this tap. So we will have this scenario in which the host OS is going to talk to VPP through a DPDK interface, E1000, which will be cross-connected to the tap interface of the virtual machine so that we can access the kernel of the stack of the virtual machine from the kernel of the host. So for this, we will use the interface L2 cross-connect command, which has a very simple syntax. So you just specify the interface from which you want to transfer and to which you want to transfer the traffic. So here I will ask VPP to forward the traffic from tab 0 to gigabit Ethernet 08 and the other way around, so that the traffic is transferred in both directions. So to check that it has been done correctly, you can do show interface address plus the name of the interface. And you will see that it has no IP address, but it is cross-connected via the layer 2 module to tab 0. And the same for tab 0, which will be connected to the gigabit internet interface. So now our interfaces are still down, so we just need to set them up. And now I should be able to ping the address of my tap from my hosts. So here I am on my host operating system, and I can go through VPP through VPP DPDK interface, which is then connected to a tap interface, which is on the host's virtual machine kernel. So in order to verify what's going on, we can use packet tracing. So as explained a bit this morning. So for this, we will ask VPP to trace an input node. So in order to know what is the name of the input node, if you don't know it, you can do show run, and you have the list of every node. So here we see that DPDK input is the node that we are interested in, as well as tab CLI RX. So if we do, for instance, trace at DPDK input 10, we will trace 10 packets from the DPDK module. So if I run my ping from my host OS, and now I do show trace, I will see the packets that have been going from DPDK. So here we can see that the packets has come onto the DPDK input node. So it is an ARP packet, Ethernet inputs. So the path in the VPP graph is the following. So DPDK inputs, Ethernet inputs, layer 2 input. And then since we have cross-connected the two interfaces, it directly goes to layer 2 output and to tap 0 outputs, where it is finally received by the kernel. Below, we see other requests. And here we see the go requests. It's okay, we have asked for 10 packets. So after you did this, you can clear trace to clear the buffer. And for instance, now if you want to trace what's going on both nodes, you can actually do the same at the same time. So if you do trace add DPDK input 10, but also tab CLI Rx 10, and then you do the ping again. When you show the trace, you will see that packets are in the correct order. So first you have a packet from DPDK, then from tap, then from DPDK again, then from tap. So you will see really that the ping is going back and forth. So this allows you to maintain the order of packets when you have different nodes that you are interested in. Okay, now just to finish with DPDK. So now if I stop VPP, you will see that the interface has not been given back to the kernel. So you can use the DPDK nickbind Python scripts, which is present in the standard DPDK distribution. So it works like by telling which PCI address you want to get back and to which driver you want to bind it to. So here, if I do this, it will take back my NIC ETH1 to the E1000 driver, which is the normal Intel driver. And now you can see that it has been brought back to the Linux stack. So if everyone is okay with DPDK, we can go to the next part of this session, which is about building and using a sample plugin. Okay, so now to the next part. So if you go to the source tree in VPP, there is a sample plugin which is called sample plugin, and so but which I've named MacSwap for the purposes of this tutorial. And so it's really it's simple and it does nothing interesting, but it's just to show off how you can use a build and write your own plugin. So what this does is like it takes all packets coming from one interface and it exchanges the source and destination hardware addresses and send it back. So it really is not very useful, but it's good for testing purposes and also to show how you can add your own node to the VPP graph, and also how you can add CLI commands, counters, APIs calls, stuff like this. So I think in the agenda of the event, the work through the code is going to be tomorrow. Here we are just going to show how to compile it and just use it so that everyone is ready to go through the code review tomorrow. So if you have used vagrants, then you have seen that there is a shared folder that is mounted when you start the VM, which takes a bit of time, which is in /vpp. So this is the folder from which you called vagrant on your host OS. And so we can use this to customize the code and compile it. So to compile the plugin, so it's simple, but there is a little glitch. We need to first copy the plugin folders in the route tree. So for some reason, the sample plugin is in the plugin subdirectory, but the build system expects it to find it on the root directory. So we just do this. This one. So now I have my sample plugin here, and we can see what is in the directory. So Makefile Stuff, and there is a subdirectory in which you have the code. So node.c being the node that we add to the graph, and sample.c is the initialization code, the CLI code, stuff like this. So to make it, well, we go to build root as we would do for normal VPP build. To compile it, you just call make VBoxNet Zero. The platform is VPP, not VPP Lite, and we will not compile the debug version, but the release one. And so you just put the name of the package that you want to compile. Then you put -install. So here, as you see, it goes into packages sample plugin.mk. So that's where it finds all the dependencies that it has to build, and also the makefiles, etc., for building the plugin. And so we can see that it has gone through all dependencies, but they were already built by the vagrant system. And finally, it configures and builds the sample plugin per se. So here we have the configure, here we have the make, and okay, here it's done. So now the plugin is located in install VPP native, which is where the binary lies. Sample plugin, lib64, sample plugin.so. So this is our shared object that we want to load with VPP. There are two ways to do this. So either you use the default directory path that is used by VPP, which is user lib VPP plugins, or you can specify in the startup configuration file in which directory you want VPP to look for its plugin. So let's go, for instance, with the first option. So I will create a directory in my home, and I will copy my SO in my home in the directory I've just created. And finally, I will go in my startup config file, and I will add plugin path, the directory. Maybe slash. So I've also put here the alternative way. So the main modifications with respect to the standard config file is here the trick to have telnet access to the CLI, here to bind a DPDK interface, and here to ask for which directory to look plugins into. So okay, now let's start VPP. So in order to show that the plugin has really been loaded, I will for once start VPP with the full path. So when you run user bin VPP, you can either specify all the arguments on the command line as arguments, or use -c and some startup file, in which case it will load the startup file and use the arguments inside. So when we do this, we see that the very first thing that is done by VPP is vlib plugin early init. So here it has found the path that we have told him, and here it loads the plugin. So what it does, in fact, is it goes into the directory, it does a DL open on each .so file, and it looks for a specific function inside to see if it's indeed a plugin for VPP. So I guess that is vlib plugin register. So it looks whether this function exists, and if it's the case, it loads the plugin. Otherwise, it just doesn't consider it as a VPP plugin, and nothing is done. So since I have here, I just quit VPP and started the normal way. So you also disable ETH1 because I've enabled it a few minutes back. And I start VPP. Connect to the CLI. I make sure that my gigabit Ethernet interface is here, which is the case. And so now we can see that the plugin has been loaded, because if we do sample, we can see that sample CLI has been created. So this is done somewhere here in the code, here. So this macro creates sample MacSwap CLI function that we are going to use for this demo. So as you see, the usage is very simple. You specify an interface name, and it enables the MacSwap plugin on this interface. So packets will be caught by the MacSwap node instead of being sent to the normal node. The MAC address will be reversed, and it will be sent back on the interface it came from. So really stupid, but easy to see if it works. So I will enable it on my gigabit interface. I put the interface up. Now I will also ask the trace module to trace 10 packets. And now I will also start a Wireshark from my Mac to see what's going on. So I will try any command that will send a packet, for instance, this ping. And we can see that the job is done. So we have exactly the same packet that comes back with broadcast as source, which is stupid, but why not? And if I go back to VPP and show trace, I see the path that has been taken in the VPP graph. So we had the DPDK input as first, and then it goes directly to the sample node, which does its job and goes to the gigabit Ethernet output back. So also, if you do show error, there has been a counter that has been created by the module, which counts the number of MacSwap packets which are processed. And finally, to disable this, because it's stupid, we can do the same command as before with disable, and this time the packets are not reversed anymore.